from the different kinds, or view of the different kinds of intermolecular forces. All right, the different kinds of intermolecular forces. So if I draw a compound here and we try to decide what kinds of intermolecular forces this compound can have, then that will be a fun game, don't you think? Okay, there it is. What do you think? What kinds of intermolecular forces does this compound have, Landon? Intermolecular forces. And if you don't know, maybe you could say, well, I don't know, but this is what I would do to start thinking about it, blah, blah, blah. So you don't need to know perfectly.
Right off the bat, I would look at the periodic table and see where silicon lies. It's a metal. I don't have it.
Okay.
Memorized yet, but,
there we go.
yeah. So, silicon is in the trans. Okay. So would it be a ion dipole force? Fall into that kind of force.
Okay, so what made you think that?
I don't think it would be a dipole force just because this compound is an ionic compound. It's consisting of a metal and a non-metal.
Okay, those are very good thought processes. However, this is not an ionic compound, actually. All right, so silicon, and that's good. You were looking at its location on the periodic table, but it's not a metal, right? What is the staircase actually itself?
Is it transition metals?
Transition metals are these ones here, our blue ones, and these are called our inner transition metals. These are actually called, and this is, not something that we have dwelt much on or learned much in Chem 105, but these are our metalloids, or semi-metals. And when they form compounds with nonmetals, it's generally going to be a molecular compound. All right? So how does that change our perspective on things, Landon?
Well, knowing now that it's a molecular compound, I'd say it falls into the dipole.
Okay. Dipole. Now, what would it matter? I mean, to have a dipole, what are the things that the molecules, what are the properties that the molecules need to have, Landon?
They need to be, I believe there needs to be polar bonding.
Okay, we need to have some polar bonding, or some polar bonds in there. And then there's a second thing that's needed. What's the other thing?
Does it need to be asymmetrical?
It does. It needs to be an asymmetric molecule. So we would need to do what in terms of identifying the symmetry?
Draw its structure.
Yeah, we need to draw its Lewis dot structure. All right, and silica looks like it's in the middle. Oxygen's here. How many electrons? Silica brings how many, Landon? 4. Oxygens. Each oxygen brings 6. So a total of 12 there. So 16 altogether. We have 2 on the board already, so we have 14 more to go. I don't know if you can see it, but I have a feeling that this compound is going to look a lot like carbon dioxide. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. See that?
Yeah.
So what does that tell us, Landon, in terms of its likelihood of forming dipole-dipole interactions with its neighbor? We were looking for symmetry, remember?
Yeah. So if we could go over the symmetry, so if we were to rotate this compound in any direction, it would still stay the same, yeah?
Yeah, I think so, right? Because we have a central atom, 2 regions of electron density bonding on the sides. So this is a linear compound. And like carbon dioxide, right? Looks a lot like carbon dioxide. Right? It's going to be a nonpolar compound, right? Silicon-oxygen bonds, yes, those are polar bonds. However, the symmetry of this resulting compound here, silicon dioxide, is going to help us realize that this is a non-polar compound. Does that make sense?
Yeah.
Excellent. So if it's not polar, then that means we can't have what?
Dipole, dipole.
No dipole dipoles. So what's left for us then?
The London dispersion force.
That's right, London forces. Very good. Now that we know that London forces are the only ones involved, and if we look at carbon dioxide, same scenario, like only London forces, right? Let's talk about which one of these would have greater London forces with its neighbor. Now, we have to remember that when we're talking about intermolecular forces, right, which is London forces, dipole, dipole, dipole ion, if it's between two different kinds of molecules, hydrogen bonding, right? All of these types of intermolecular forces are referring to the interaction that occurs between a molecule and another molecule of itself, right? That's what we're talking about. So, what do you think? Which one of these, silicon dioxide or carbon dioxide, is going to have greater intermolecular forces with itself, right? With a neighboring compound of itself. And you know, the questions on the tests won't be that clarified. They'll just say, which one of these has greater intermolecular forces? All right? But they're always referring to with another molecule of itself, right? All right, Harry, do you have any ideas? We didn't really talk about this, but you might have learned something from your homework. Any ideas for this, Harry? Which one of these has greater intermolecular forces? We've decided that they both have to be London dispersion forces, but can you think of which one might be greater?
I only remember last time we learned that structure had something to do with it.
Okay.
But they both share the same structure, so I'm not sure what you would do in this situation.
Okay, good. So yeah, I think that what you're referring to is if I had a compound that had C5H12, for example, and had 5 carbons, 1, 2, 3, 4, 5, all in a chain, that would have a different boiling point than a C5H12 compound that looked like that. Is that what you're referring to, Harry?
Yeah.
Uh-huh. Very good. Very good. Now we're going to throw in one more component that will differentiate the amount of London forces compounds have. Okay? By drawing out kind of roughly this compound and this compound. Silicon dioxide, if I were to draw, well, let's draw carbon dioxide first. If I were to say, okay, here's the electron density around the carbon. Whoops. Here's the electron density around the carbon. Here's the electron density around the oxygen, one oxygen, and there's the electron density around the other oxygen. And maybe this roughly indicates kind of its structure and electron density. How would it differ for silicon dioxide? How would it differ if I'm going to draw it up here? Harry, what do you think? How would I draw these circles differently, maybe?
Would silicon be... I'm sorry, I'm not sure.
Silicon would be, and I don't know if this is what you're thinking of, but it would be much larger than carbon, don't you think?
Because it's more electronegative.
Well, it's not more electronegative, it's just a larger atom. It has 3s2 and some 3p electrons, whereas carbon just has 2s2 and 2p electrons. So silicon would be larger, not a ton larger, but it would be larger. Okay? It would be larger. Now, we didn't talk about this, but any ideas in your mind, Harry? Is there any reason why this larger one might have more London forces with a neighboring compound?
Is it because it has more protons, so it pulls it towards it more?
Well, it could be that. What it actually has to do with is because this circle is larger, when there is a movement of the electron density, right? So let's say it moves over here temporarily, right? Because there's a larger space that's moving, it results in a larger net kind of induced dipole. It's a temporary dipole, but because there's more electrons to move, then you get a greater induced dipole. Whereas this one here, if it moves the same amount, it's just a movement of less electron density. So, let's see if that made any sense. Brielle, or we'll stick with Harry here. Harry, which one of these has greater London forces between it? Silicon dioxide or carbon dioxide? Silicon dioxide, that's right. And so another way to generally think about that, just like we said with carbonaceous compounds, right? We said C5H12 compared to, let's say, C8H18, carbon 1, 2, 3, 4, 5, 6, 7, 8. Brielle, which one of these did we say would have the greater number of greater amount of intermolecular forces? The pentane or the octane? That's the octane, that's right. And that was simply because it was a larger compound. Well, the increased mass of the compound can occur or can make a difference as well, even if it's just on a single atom like that. All right. We also see this trend, right? If you look at the boiling point of helium compared to the boiling point of argon, compared to the boiling point of xenon, for example, what do you think, Sarah? Which one of these is going to have a higher boiling point? That's right. Higher boiling point. Xenon is going to have a higher boiling point, and that's simply because why, Sarah? That's right. That's right. It's larger, and so now I'm going to use that circle that I've drawn as a kind of indicator of the size, right? It's larger, therefore, when a neighboring molecule, or not molecule, it's an atom here, right? These are just individual noble gases, right? So when a neighboring atom comes nearby, if this one shifts, there's more of a movement of the overall electron density, and so there's more of a likelihood of the other one being able to take advantage of that. So just sheer mass can be another way of indicating increase in intermolecular forces when you're talking about London forces. Okay, let's see if we can answer some of these problems here now. How about this one, Alyssa? Which of the following is not a true statement? Everybody take a look at this one and think about it. Give us about 3 seconds, Alyssa. Okay, any ideas?
Well, I know it's not B.
You know it's not which one?
I know it's not B because we just talked about that.
Okay, so you know B is true. The greater the mass, the greater the London force.
I think it's C.
Another name for London forces is induced dipole attraction.
Yeah, I think that's wrong.
Okay, let's look at A. What does A say? Only nonpolar molecules exert London forces. Why would that be, Alyssa? Are any ideas, or are you just kind of guessing at this point?
Aren't London forces symmetrical?
Symmetrical?
Like the molecules are symmetric, so they don't have, they're nonpolar overall.
Okay. So, and this is a very good thing and important that we recognize this. And this is, kind of a ticky-tack thing, but people love to still talk about it. But London forces are the most predominant intermolecular forces when you're talking about a nonpolar compound. Because if it's nonpolar, then you don't have dipole-dipole, and you don't have hydrogen bonding. So all it's got going for it is London forces. All right. If you're thinking of something like water, H2O, right? We got dipole-dipole, we got hydrogen bonding. Now, does that mean for any reason that the London forces are gone? And it doesn't mean that. It doesn't mean that. It still can have London forces, even though it has dipole-dipole or hydrogen bonding, as in this case. London forces can still be a factor. Now, are they going to be an influencing factor? Not very much compared to the amount of energy that is in a hydrogen bond or a dipole-dipole bond. But still, it doesn't mean that London forces can't occur. Okay, so A and B are true. Which one following is not a true statement? Oh, no, sorry. A is not true. Only nonpolar molecules exert London forces. That's not true. Nonpolar molecules have London forces, but polar or compounds that have dipole-dipole or compounds that have hydrogen bonding also have London forces influencing them as well. So the one that, which of the following is not a true statement, that is A. So that means another name for London forces is induced dipole attraction. Now, I don't know, Jace, can you help us kind of with our English here? What does induced dipole meaning when they say induced dipole? What's that talking about?
I would think that like it just helps facilitate like dipole attractions. So maybe like it's a weak bond and it brings them like temporarily together, so that allows the dipole attraction to be like set.
Okay, very good. So let me make sure I help you guys know why they are also called induced dipole attractions. Okay, the reason is, let me make sure that this goes up for this there. If I have my, let's see here, let's go back to my slot machine, right? If I have my slot machine situation here, whoops, go back one more. Here we go. If I have my slot machine here and I stop it at any given moment, all right, if, for example, the electron density over here is kind of moving towards this molecule a little bit, that's bringing negative charge. And what that can actually do is that movement of negative charge can induce these ones, the electron density around these atoms, the nuclei, to move away. So as one cloud of electron density roams toward another molecule, it will cause that temporary dipole to a degree because the electron density here will be repelled by it. Does that make sense, Jace?
Yeah.
Okay, so essentially what we're saying here is, to a degree, those London forces can be caused by the fact that they're moving. In fact, we get something that's called electrons synchronizing with each other. Now, this is an exaggeration, but essentially what happens is you get multiple molecules behaving as kind of like one in terms of the motion of their electron density, because as they move, they influence the movement of their neighboring molecules. Okay, so this doesn't necessarily happen exactly like this, but the idea is you can induce the movement of electron density and create this dipole by inducing it from one molecule to another. Okay, good. How about this question here? Can we identify the kinds of intermolecular forces present in the following compounds and then rank them in order of increasing boiling point? Rank them in order of increasing boiling point. Okay, I'm going to break you guys up into groups here, and we're going to let you guys talk about this for probably just about 2 minutes. Okay, let's see. There we go. All right, go for it. All right, very good. So, whose turn is it? Taewon, did you get to talk about it in your group? A problem with the software, or you guys couldn't determine? A washing machine problem? Okay, connection problem. Well, Taewon, what do you think? if we take a look at this compound, SH2, what kind of London forces would you expect between two molecules of SH2? Okay. Can you help him out, Harry? What do you think?
What's the question? What kind of molecule would it be?
What kind of intermolecular attractions would occur between two molecules of SH2?
So that would be London forces and dipole-dipole.
Okay, very good. You always have London forces, right? All molecules are going to have London forces, we decided. And then our dipole-dipole, because this is an asymmetrical molecule and it has, a polarity associated with sulfur and hydrogen. What about hydrogen bonding, Harry? Did you not include that one or what?
It doesn't have hydrogen bonding because it's not nitrogen, oxygen, or fluorine.
Okay. You get the augmented dipole-dipole when that hydrogen is losing its electron density to either a nitrogen, oxygen, or fluorine, because those are the electron hogs. Okay, very good. What about this one here, Brielle? Methanol.
London, dipole, dipole, and hydrogen bonding.
Okay, very good. Very good. Hydrogen bonding, dipole, dipole, and hydrogen bonding is, you won't find a scenario generally where they ask you to identify both of those because it is an augmentation of dipole, dipole. But that's right. Hydrogen bonding is a strong type of dipole, dipole that's occurring here, and then we also have our London forces. Okay, Sarah, this CBr4.
I believe it just has London forces.
Okay, that's right. This one, and then neon also just has London forces, Sarah. Which one of these would have greater strength of London forces, Sarah? Carbon tetrabromide or neon?
Probably carbon tetrabromide.
Okay.
Because it's bigger.
Because it's bigger. That's right. So, if that's our case here, then because our molecular mass, right, helps us indicate the difference between those, our strongest intermolecular force would be the hydrogen bonding occurring on methanol, and then our dipole-dipole, and then our London forces, as Sarah described. All right. Any questions about that? Okay. Let's go on to here then. Let's arrange these in increasing strength of intermolecular force. And then after you've looked at this for about 18 seconds, Jace will tell us an answer. Okay, so get ready, Jace, to tell us which one of these is correct. Or I guess it says none of these, I guess is a possibility as well. Okay, ready, Jace?
Yeah, I would go with C, just because I would think that the hydrogen fluorine is the only polar molecule, I think.
Okay, so that one seems to have to be the strongest.
Yeah.
I'd agree with that. Are we sure with this CH4 and the CO2 bit down here? What kind of intermolecular forces do we have to worry about for CH4 and CO2?
Well, I know CO2 is going to be symmetric, so I know that's not going to be polar, and the CH4 is symmetric too, so there's not going to be dipole, and there's not going to be dipole for either one of those, so you're just going to have to worry about London forces. So I guess you'd have to check the weights of those respective molecules, and I would obviously it's 16 for CH4, and it's going to be 32 plus 12, so 44 for the CO2. So the CO2 is actually going to have stronger intermolecular forces
Okay, very good. So the
So I
order,
guess not-
what's that?
Yeah, I was just agreeing with D, I guess. Yeah.
So we knew that the last two that only had London forces, that our only way to distinguish them was going to be our the molar mass, the mass of the materials, of the compounds. Okay, excellent. Good review there.